In 1957, every warship on Earth ran on the same fuel. Not fear, not steel, oil. Every cruiser, every destroyer, every carrier, and every navy on the planet carried a fixed number of gallons in its bunkers. And when those gallons ran out, the ship stopped being a weapon and became a target. Fleet commanders planned entire wars around this one constraint. Task forces broke formation to meet oilers at sea. Admirals counted miles the way gamblers counted chips, because range wasn't a design feature. It was a leash. The United States Navy had lived by this leash since the age of sail gave way to the age of steam. It was not a limitation anyone questioned. It was gravity. You didn't debate gravity. You built around it. Then, in a shipyard on the Fore River in Quincy, Massachusetts, a keel went down for a ship that broke the leash entirely. It had no need to refuel, not once, not for years. It carried no smokestack because it had nothing to burn. And bolted to its superstructure was a radar system so radical that no one, including the engineers who built it, fully knew if it would work. The United States Navy's own surface warfare officers looked at this ship and asked a question that would take a decade to answer. What if the future the Navy just built was a mistake it couldn't afford? 3 years earlier, in 1954, a 54-year-old engineer named Hyman Rickover had already proven the impossible could float. His submarine, USS Nautilus, ran on a nuclear reactor instead of diesel engines and batteries, and it could stay submerged not for hours but for weeks. The world's navies took notice. The Soviet Union took notice. The United States Congress took notice and started writing checks. By 1956, Rickover's Naval Reactors program was no longer an experiment. It was an institution inside an institution, answering to both the Navy and the Atomic Energy Commission, immune to the normal chain of command, and expanding fast. Submarines were only the beginning. The next question was obvious, and dangerous. Could a reactor built for a boat that hides also power a warship built to be seen? On October 15, 1956, the Navy placed the order that would answer it. Not for another submarine. Not yet for the nuclear carrier still on the drawing board. For a cruiser, a large gun and missile surface combatant, the kind of ship that patrols, escorts, and shows the flag in open water. Every day, for years. A cruiser had never needed a reactor before. Cruisers were not stealthy. They did not need to vanish. What they needed, according to the officers who ran the surface fleet, was speed, firepower, and a hull the Navy could afford to build more than one of. Rickover wanted to prove that nuclear power belonged everywhere the Navy sailed, not just underwater, not just on a supercarrier already justified by the size of its air wing, but on an ordinary-sized combatant that had to earn its reactor on the numbers alone. Those numbers were brutal from the start. A conventional cruiser of the same era cost the Navy somewhere in the neighborhood of $60 to $70 million. This one, not yet named, still just a hull number, CLGN 160, was already being quietly estimated at more than 4 times that. No one outside the program office knew the final figure yet. Everyone inside it suspected it would be worse. The keel went down 14 months later, on December 2, 1957, at the Bethlehem Steel Yard on the Fore River. The ship being built there had a name waiting for it. Long Beach, after the California city that had sponsored a Navy cruiser before. What nobody in that yard could yet say, not the shipwrights welding the hull plates, not Rickover's engineers checking reactor tolerances, not the admirals who'd approved the order, was whether the ship would justify its own price tag before the surface Navy's patience ran out. Shipwrights who had spent careers building cruisers looked at the drawings for Long Beach and didn't recognize what they were looking at. There was no smokestack. Not a small one. Not a disguised one. None at all. Every warship afloat, back to the ironclads, vented smoke from burning fuel through a stack, and that stack shaped the whole silhouette of a ship. Long Beach burned nothing. A nuclear reactor doesn't exhaust smoke. It generates heat through fission, and that heat drives the turbines directly. Remove the fuel, and you remove the reason for the stack. For the first time in the history of steam and steel navies, a major warship's profile wasn't dictated by combustion. It was dictated by something invisible. In its place, rising from the middle of the ship, stood a superstructure unlike anything the surface fleet had built before. A flat-sided, almost rectangular tower, tall enough to house the largest bridge of any warship in the world. Sailors would later joke that it looked less like a cruiser and more like a floating office building. That shape wasn't an accident or an aesthetic failure. It was structural necessity, built to carry a piece of technology the Navy had never put to sea. Bolted to those flat sides were the antennas of a system called SCANFAR, 2 radars. The AN-SPS-32 and the AN-SPS-33, developed by Hughes Aircraft. A conventional radar works by physically rotating a dish, sweeping up the horizon one narrow slice at a time. SCANFAR's antennas didn't rotate at all. They were fixed, flat panels, electronically steering their beams across the sky by adjusting the timing of the signal itself, a technique called phased array scanning. In theory, it meant Long Beach could track multiple aircraft and missiles simultaneously, in every direction, without ever turning a single moving part. In theory, it was the ancestor of every modern naval radar system that would follow it, including the Aegis system that still defends American warships today. In practice, in 1959, it was untested at sea, built around thousands of vacuum tubes, and it drew a punishing amount of electrical power just to stay on. The ship carrying this equipment was, in its own right, a break from everything that came before it. Long Beach was the first cruiser the Navy had designed and built entirely new, from the keel up. Since before the Second World War, every prior post-war cruiser had been a wartime hull, finished late or modernized old. She would also be the last ship in American naval history to be laid with traditional teakwood decking, a small detail that marked her, even at her launch, as something already caught between two eras of shipbuilding. Construction did not go quietly. At the Fore River Yard, workers discovered that anti-mine electrical cabling running through the hull had been deliberately cut, not once, but in 3 separate locations. The Navy never publicly resolved who was responsible or why. The damage was repaired, the work continued, and the incident passed into the ship's history as an unexplained footnote rather than a solved case. On July 14, 1959, Long Beach slid down the ways at Quincy, sponsored by Marion Swanson Hosmer, and entered the water as the strangest-looking major warship the U.S. Navy had ever produced. No stack, a skyscraper for a bridge, and a radar system that even its own builders weren't certain would work once it left the harbor. She would not be commissioned for another 2 years. And by the time she was, the argument over whether any of it had been worth the cost was only just beginning. The opposition to Long Beach did not come from Congress, and it did not come from a rival navy. It came from inside the United States Navy itself, from the surface warfare officers whose careers were built on cruisers and destroyers, and who watched Rickover's program absorb budget, priority, and institutional attention that had once belonged to them. Their argument was not reckless, and it was not petty, it was arithmetic. A nuclear reactor earned its cost on a submarine because a submarine's entire tactical value depended on staying hidden and staying submerged. The reactor didn't just extend the boat's range, it defined what a submarine could be. A nuclear reactor earned its cost on a carrier, even at a staggering price, because a carrier's air wing generated enough combat power that the extra decades of fuel-free operation could be justified against the alternative, risking a carrier group's survival on a trail of oilers in the middle of the Pacific. A cruiser was neither. A cruiser's job was escort, patrol, and gunfire support, work that oil-burning ships had done adequately and cheaply for a generation. Surface warfare officers pointed to the numbers with a bluntness that Rickover's own submariners rarely had to face. For the price of a single nuclear cruiser, the Navy could build 3, sometimes 4 conventional cruisers of comparable firepower. 4 hulls patrolling 4 different oceans, they argued, protected American interests better than one nuclear-powered showpiece patrolling one. There was a second front to the skepticism, quieter but sharper inside the engineering community, the radar. Scanfar had never been proven at sea. Its vacuum tube electronics were known, even before Long Beach's keel was laid, to be power-hungry and maintenance-intensive. Radar officers who had spent their careers on mechanically rotating systems, reliable, well understood, easy to repair with parts already in the Navy's supply chain, questioned why the service was betting a flagship-class cruiser on a technology that existed, as of 1959, almost entirely on paper and in prototype testing at a Hughes aircraft facility in California. The two doubts fed each other. If Scanfar failed, critics argued, the Navy wouldn't just have an expensive radar problem. It would have proof that the entire premise of Long Beach was flawed. An enormous singular investment in unproven technology, wrapped around a reactor whose advantages didn't apply to the ship's actual mission. Rickover, by every account of officers who dealt with him directly, treated this opposition the way he treated most institutional resistance, as noise to be outlasted, not an argument to be won in committee. He did not campaign publicly against the surface warfare community's objections. He simply kept building, protected by direct access to Congress and to the Atomic Energy Commission, access that made him largely insulated from the normal Navy chain of command that his critics still had to answer to. That insulation was itself a source of resentment. Officers who had spent decades earning promotions inside the surface Navy's ordinary structure watched a program run almost entirely on Rickover's personal authority, absorb funding at a scale their own commands could never compete for. The objection was rarely phrased as jealousy in official memoranda. It was phrased as fiscal responsibility, as operational priorities, as questions about whether one man's judgment should carry more weight than the Bureau of Ships' collective analysis. But underneath the paperwork, colleagues of both men would later describe something closer to institutional exhaustion. A surface Navy tired of being told, budget cycle after budget cycle, that the future belonged to the reactor program and not to them. By the time Long Beach was ready for her sea trials in the fall of 1961, the ship had already become something more than a vessel under construction. She was a proxy argument for an entire philosophy of naval investment, a single hull carrying the full weight of a question the surface warfare community wanted answered, before the Navy built a second one. Was this genuinely the future of the fleet? Or was it one admiral's very expensive experiment dressed up as one? Nobody in the Navy's surface warfare offices expected the ship's first years at sea to hand them an easy answer. And they didn't. On September 9, 1961, at the Boston Naval Shipyard, USS Long Beach was commissioned into the United States Navy under the command of Captain Eugene Parks Wilkinson, a name that already carried weight in the nuclear fleet. 6 years earlier, Wilkinson had been the first commanding officer of USS Nautilus, the boat that started the entire program. Putting him in command of Long Beach was not a casual assignment. It was the Navy signaling, through its choice of captain, that this ship belonged to the same lineage of firsts, and it was, without qualification, a first. Long Beach entered service as the world's first nuclear-powered surface combatant, not a submarine, not an experiment confined to a test basin, but a fully armed, forward-deployed warship, assigned to the Atlantic Fleet and homeported at Norfolk, Virginia. At over 15,000 tons and more than 720 feet long, she was, at the moment of her commissioning, the largest non-carrier surface combatant in the world. She was also, in one respect, an unfinished argument. Long Beach was commissioned without her intended gun armament installed, a guided missile cruiser built almost entirely around missiles and radar, with no significant gun battery to speak of. That gap became public 7 months later, in April 1962, when President John F. Kennedy visited the ship. According to Navy accounts of the visit, Kennedy's reaction to a warship with no guns led directly to an order. 2 5-inch guns were added later that year. Even the president, touring the Navy's newest and most expensive cruiser, had looked at her and seen something missing. From October through December of 1961, Long Beach ran an extended shakedown cruise. The sea trials meant to test every system on a new warship simultaneously: propulsion, weapons, and above all, the untested Scanfar radar suite bolted to her superstructure. This was the moment the surface warfare skeptics had been waiting for. A shakedown cruise doesn't just test whether a ship can sail. It tests whether the promises made on paper survive contact with open water. The reactor performed exactly as Rickover's program had promised. That part of the ship's premise, at least, was no longer theoretical. Nuclear propulsion worked. On a surface combatant, in real operational conditions, immediately. The radar was a different story. Scanfar's fixed, electronically steered antennas required a scale of power draw and a density of vacuum tube electronics that no ship's crew had ever had to maintain at sea before. Reliability issues surfaced almost immediately, the same class of problems that would later plague the identical system installed aboard the carrier Enterprise. For a Navy audience already primed to doubt the ship's cost-effectiveness, these early stumbles were not a footnote. They were confirmation. By early 1962, Long Beach was a ship of two unequal truths. Her reactor had answered the engineering question decisively. Nuclear power could run a full-size surface combatant, indefinitely, without a single stop for fuel. Her radar had not yet answered anything, except that the leap from prototype to warship had been more difficult than Hughes Aircraft's engineers, or the Navy that bought their system, had accounted for. The surface warfare officers who had questioned the entire program from the start now had something concrete to point to. Not speculation about cost overruns. An actual documented ongoing reliability problem on the actual ship, in the actual fleet. The next several years would decide which of Long Beach's two truths the Navy would remember. For roughly the first half of the 1960s, USS Long Beach lived inside a contradiction the Navy struggled to resolve. A ship whose most important system worked perfectly, carrying a radar suite that, by comparison, seemed almost designed to fail. The AN/SPS-32 and AN/SPS-33 radars, together known as Scanfar, were built around vacuum tube technology, the same basic electronic components used in radios and early televisions of the era, arranged by the thousands into arrays that had to function in constant synchronization. Each tube was a potential point of failure. On a ship at sea, in salt air, under continuous vibration from engines and weather, that meant a maintenance burden unlike anything the surface Navy's radar technicians had trained for. Rotating radars, the kind every other cruiser and destroyer in the fleet still carried, had one moving mechanical assembly that crews understood, could inspect visually, and could repair with parts already standardized across the fleet. Scanfar had no rotating parts at all, and that was precisely the problem. Its complexity was hidden inside fixed panels, inaccessible without specialized diagnostic equipment and training that, in the radar's earliest years of service, barely existed outside the Hughes Aircraft engineers, who had built the prototype. The power demand compounded the issue. Scanfar drew an amount of electricity that strained Long Beach's onboard systems, competing directly with the ship's other combat electronics. Crews reported that keeping the radar fully operational for sustained periods required more careful power management than any other system aboard the ship, an irony not lost on officers who had once questioned whether a nuclear reactor's near-limitless power supply was even necessary for a cruiser. It turned out the reactor wasn't just useful. It was one of the only reasons Scanfar could run at all. None of that solved the reliability problem itself. Throughout the ship's early deployments, Scanfar's performance was inconsistent. Periods of full functionality, interrupted by tube failures, calibration drift, and maintenance downtime that pulled the radar offline exactly when a warship's sensors mattered most. The Navy's own internal engineering assessments, echoed years later in post-war analysis published by the U.S. Naval Institute, would describe the SPS-32 and SPS-33 in blunt terms. Plagued by maintenance and reliability problems from the start, for the surface warfare officers who had opposed the entire nuclear cruiser concept since 1956, this was not an abstraction anymore. It was the exact failure mode they had predicted, playing out in real time, on the one ship built to prove them wrong. The criticism sharpened. If the Navy's showcase investment in next-generation radar couldn't reliably track targets, what exactly had the extra hundreds of millions of dollars bought, beyond an unlimited fuel supply the ship's actual mission didn't obviously require? The failure reached beyond Long Beach alone, which made it harder to dismiss as a single ship's bad luck. The same SCANFAR system, installed on the nuclear carrier Enterprise, suffered nearly identical problems: enormous power draw, constant tube maintenance, and reliability that never matched the concept's promise. A parallel related program made the pattern impossible to ignore entirely: the Navy's Typhoon missile system. Built around an even more ambitious phased array radar called the ANSPG-59, ran into cost overruns and technical failures, so severe that the entire program was canceled in 1963 before a single production unit reached the fleet. Typhoon and SCANFAR were not the same system, but they shared a lineage, the same reach for a technology that outpaced what 1950s electronics could reliably deliver at sea. When Typhoon collapsed, it cast a long shadow backward onto Long Beach's own radar, reinforcing exactly the argument her critics had made from the beginning. The Navy had moved too fast, on too many fronts, toward a phased array future the underlying electronics weren't yet mature enough to support. Inside the surface warfare community, the verdict, for the time being, felt settled. The reactor worked, the radar did not. And a warship, ultimately, is judged by whether it can find and track its targets, not by how long it can stay at sea without refueling, if it can't see what it's shooting at once it gets there. What none of Long Beach's critics fully accounted for, in these years of documented radar failures and mounting frustration, was a second question the ship was quietly answering at the same time, almost by accident, one that had nothing to do with radar at all, and everything to do with what a warship could do when it never had to stop. Long Beach was never going to be judged by her own service record alone. She was the opening argument in a fight over what the entire United States surface fleet would look like for the next generation, and that fight ran for nearly 2 decades after her keel first went into the water. The Navy did not stop with one ship. A year after Long Beach commissioned, the frigate USS Bainbridge followed in 1962, then the cruiser Truxtun in 1967, then 2 ships of the California class in the mid-1970s, then 4 more of the Virginia class by 1980. 9 nuclear-powered surface combatants in total, spread across nearly 2 decades, proof that the program had survived its early critics. But 9 ships, built 1 and 2 at a time over 20 years, was not what Rickover had originally envisioned. It was not a fleet, it was a trickle. The reason was the same one the surface warfare skeptics had raised back in 1956. Now backed by 2 decades of operating data instead of speculation. Each midlife refueling overhaul for a nuclear cruiser, pulling the reactor apart, replacing the core, putting the ship back together, cost the Navy somewhere between $200 and $300 million, in an era when that sum could buy an entire additional conventional destroyer. Later Navy analysis would calculate that nuclear cruisers ran 20 to 30% more expensive over their full service lives than the fossil fuel ships of comparable firepower. The endurance the reactors provided was real. What was the bill for maintaining it? By 1975, the Navy made its decision. Procurement of new nuclear-powered cruisers was halted after that fiscal year. Not canceled with an announcement, but simply allowed to stop. The budget lines quietly closed. The moment of truth came a few years later, when the Navy sat down to design its next generation of missile cruisers, the ships that would carry the new Aegis combat system. 2 nuclear-powered options were on the table: a large, purpose-built strike cruiser, and a smaller design derived from the existing Virginia-class hull. Both were rejected. The Navy chose instead to put Aegis on a conventionally powered hull already in production for the Spruance-class destroyers, a decision that became the Ticonderoga class, the backbone of the American surface fleet for the rest of the century. There was a final, almost ironic twist to the story, and it involved Rickover directly. In the 1970s, there were serious proposals to upgrade Long Beach herself with the new Aegis system during a scheduled overhaul, to give the very first nuclear cruiser the very newest radar, and make her case for the future all over again. According to officers who worked the proposal, it was Rickover's own resistance that helped kill it. He reportedly worried that making the existing nuclear cruisers more capable would undercut the argument for building new ones. Why fund another nuclear hull if the old one could simply be upgraded instead. The logic protected nothing. Long Beach never got Aegis. Neither did her half-sister Arkansas, the last nuclear cruiser ever built. And no additional nuclear cruisers were ever ordered again. The man who had spent 30 years insisting that nuclear power belonged everywhere the Navy sailed had, in trying to protect his program's future, helped close the door on it himself. By the end of the 1970s, the numbers had answered the question the surface warfare officers first asked in 1956. Just not the way anyone on either side had expected. Nuclear power was not too unreliable to build a surface fleet on. It was too expensive to build one at scale. And the ship that had started the entire argument was still out there. Sailing. Unlimited in range. Carrying a radar system already a full technological generation behind the fleet she had once been built to lead. While the surface warfare community kept its eyes on Scanfar's failures, Long Beach was quietly answering a different question. The original one. The one Rickover had bet an entire career on back in 1956. And the answer arrived not in a committee room, but in the middle of the ocean. On July 31, 1964, Long Beach departed on a mission unlike anything the U.S. Navy had ever attempted. Task Force 1, the carrier Enterprise, the frigate Bainbridge, and Long Beach herself, set out to circumnavigate the globe. Not with a supply train trailing behind them. Not with a single scheduled stop for fuel. 3 nuclear reactors. 3 ships. 1 continuous voyage around the entire planet. It was called Operation Sea Orbit, and it was designed from its first day to be seen. This was the height of the Cold War, and the Navy wanted the Soviet Union to watch 3 American warships cross every ocean on Earth without once asking anyone for oil. For 65 days, the task force sailed roughly 30,000 nautical miles, through the Atlantic, around the Cape of Good Hope, across the Indian Ocean, through the Pacific, and came home having never touched a fuel line. This was the leash the entire Navy had lived under since the age of sail. Sea Orbit didn't argue against it. It simply demonstrated, in front of the whole world, that the leash no longer applied to at least 3 American ships. No oiler had shadowed them. No refueling rendezvous had dictated their route. For the first time in naval history, a battle group's operational range was not a function of its fuel bunkers at all. The radar critics had a point about Scanfar, and nothing about Sea Orbit changed that point. But Sea Orbit was never about the radar. It was about the reactor. And on that question, the answer was now written across 30,000 miles of open water, filmed, photographed, and broadcast home as proof that nuclear propulsion had already changed what an American warship could do. 4 years later, Long Beach delivered a second kind of proof. This one under fire, not under cameras. On May 23, 1968, on station in the Gulf of Tonkin, Long Beach's crew tracked a North Vietnamese MiG-21 far beyond the range any ship's gun could have touched. They fired a Talos surface-to-air missile, a weapon guided not by Scanfar, but by its own separate tracking radar, and the missile found its target at a range of roughly 65 nautical miles. The MiG went down. A second aircraft flying through the wreckage was destroyed as well. It was the first time in naval history that a hostile aircraft had been shot down by a missile fired from a ship at sea. 4 months later, in September 1968, Long Beach did it again, downing a second MiG at 61 miles. These were not abstractions written into a procurement study. They were kills, logged, dated, and confirmed. Proof that the missile systems built around Long Beach's design could reach further and hit harder than anything a conventional cruiser of the era carried. The ship that critics had spent years describing as an expensive answer to a question nobody had asked was now the only warship in the world that had actually answered it, twice, in combat. None of this repaired Scanfar. The radar's reliability problems would continue for another decade, and the system would eventually be stripped from the ship entirely. But by the end of the 1960s, it was no longer possible to describe Long Beach as a single failed experiment. She was, at the same time, a radar disappointment and an operational milestone. A ship whose worst system and best system happened to sit inside the SWAM hull. Built by the same program, funded by the same contested dollars. The surface warfare officers who had opposed her in 1956 had been right about the radar. They had not been right about everything else, and history, when it finally wrote the verdict on Long Beach, would have to hold both truths at once, because neither one erased the other. Long Beach herself never got a sister ship. The Navy built her once, tried variations of her Formula 8 more times across 2 decades, and then stopped. But an engineering legacy doesn't require a second hull to survive. It survives in the reactors, the radars, and the institutional experience that outlives any single ship. And on all three counts, Long Beach's fingerprints run further than her own 33 years of service ever suggested they would. Start with the reactor. Long Beach ran on a design called the C-1W, built by Westinghouse specifically for a cruiser, engineered closely alongside the A-1W and A-2W plants, developed for Enterprise around the same period, was, in the Navy's own reactor taxonomy, a one-off, the only cruiser-class reactor of its kind, never repeated, with every subsequent nuclear cruiser, instead using a different destroyer-derived design called the D-Series. But the C-1W wasn't wasted engineering. It was part of the same continuous body of work Rickover's Naval Reactors program was building across every hull it touched. Data on core longevity, on operating a pressurized water reactor continuously at sea for years at a stretch, on training crews to run a power plant that had to work perfectly with no possibility of walking away from it mid-ocean. That accumulated experience fed directly into the reactor lineage that eventually produced the A-4W. The design Westinghouse built for the Nimitz-class supercarriers, the ships that have formed the backbone of American carrier aviation since 1975 and remain in service today. Long Beach wasn't the ancestor of the Nimitz reactor in a straight line. She was one of the 2 or 3 programs running in parallel that made the entire family of surface ship reactors possible in the first place. Proof, logged and refueled and reproven at sea, that the Navy could run a power plant this complex on a warship without a submarine's hull to protect it. The radar told a similar story, in reverse. ScanFar itself never got fixed. The Navy pulled the AN-SPS-32 and AN-SPS-33 arrays off Long Beach in 1982, replacing them with a conventional rotating radar during a major overhaul. A quiet admission, 20 years after commissioning, that the fixed array experiment on this particular hull had run its course. But the underlying idea, a radar with no moving parts, steering its beam electronically instead of spinning a dish, didn't die with ScanFar. It waited for the vacuum tubes to be replaced by solid-state electronics reliable enough to make the concept work. That successor arrived as the AN-SPY-1 radar, the heart of the Aegis combat system, first fielded in 1983 and still, in updated form, standing watch aboard every Arleigh Burke-class destroyer and Ticonderoga-class cruiser in the fleet today. Naval historians and the engineers who built Aegis have been direct about the lineage. ScanFar was the failure that had to happen before Aegis could succeed. Long Beach's radar didn't work, but it proved, in painful and expensive detail, exactly which problems the next version would need to solve. Even the institutions around Long Beach didn't survive intact. The Bethlehem Steel Yard on the Fore River in Quincy, Massachusetts, the yard that laid her keel in 1957 and launched her in 1959, closed for good in 1986. One more casualty of an American commercial shipbuilding industry that contracted sharply in the final decades of the Cold War. The company that built the first nuclear-powered surface warship in history no longer builds ships of any kind. And the ship herself, decommissioned in 1994 and stricken in 1995, never became the museum many naval historians wanted her to be. Removing a warship's nuclear reactors is not optional and not simple. By the early 2020s, Navy estimates for fully recycling her hull ran into the hundreds of millions of dollars, a bill directly tied to the same technology that had once made her the most advanced cruiser on Earth. A large section of her hull, containing her propulsion spaces, remains in storage at the Puget Sound Naval Shipyard in Washington State to this day, neither scrapped nor preserved, waiting Taken together, the through line doesn't run in a straight line from Long Beach to any single ship sailing today. It runs instead into two of them at once. The reactor lineage that keeps Nimitz-class carriers at sea for 50 years without refueling, and the radar lineage that lets an Aegis destroyer track 100 targets simultaneously without ever turning a dish. Long Beach was the one ship built to prove both ideas could share a single hull. It took the rest of the Navy another 20 years to prove she'd been right about which one mattered more. And by then, there was no one left building the kind of ship that could have carried both lessons forward at once. By any honest accounting, both sides of the argument that began in 1956 turned out to be correct. And that is precisely why the argument never really ended. Even after the Navy stopped building the ships, the surface warfare officers who doubted Long Beach from the start were right about the radar. A Scanfar never became reliable. Drained power the ship could barely spare, and had to be torn out after 2 decades of service. They were right, too, about the arithmetic. Nuclear cruisers cost more to build, cost far more to maintain, and by the Navy's own later analysis, ran 20 to 30% more expensive across a full service life than the conventional ships they were built to outclass. When the Navy finally chose the next generation of missile cruisers in the late 1970s, it chose a conventional hull, the Ticonderoga class, over every nuclear option on the table. 9 nuclear surface combatants were built across 2 decades. Then the Navy simply stopped and never started again. On paper, in dollars, that looks like a verdict against the entire premise Long Beach was built to prove. But Rickover and the reactor program were right about something the balance sheet never fully captured. Unlimited range was not a luxury feature. It was twice demonstrated as a strategic weapon in its own right. Once in 1964, when 3 nuclear-powered ships circled the entire globe without a single stop for fuel, broadcasting American technological reach to a watching Soviet Union. And again in 1968, when Long Beach's missiles reached out 65 miles across the Gulf of Tonkin and did something no ship's weapon had ever done in the history of naval combat. Cost is measurable in dollars. Reach, in those 2 moments, was measured in something the Navy's budget analysts had no column for. The honest verdict is not that one side won the argument. It's that the Navy built exactly one ship capable of settling it. And the answer she delivered was more complicated than a budget office or a radar technician could have predicted alone. The reactor justified itself in ways no cruiser had ever needed justifying before. The radar failed in ways expensive enough to nearly discredit the entire idea it was attached to. Both things were true. In the same hull, at the same time, which is exactly why the Navy spent the next 20 years trying, and ultimately failing, to build a second ship that could keep proving the first half of that sentence without repeating the second. Long Beach outlived the argument that built her. She served for 33 years, through Vietnam, through the Cold War's final decade, through a modernization that never came, past the point where anyone still debated whether she should have been built at all. She was decommissioned in 1994, stricken in 1995, and today survives only as a section of hull in storage at a naval shipyard in Washington state. Neither a museum piece nor scrap metal. Unresolved in death the way she had been unresolved for most of her service. The Navy that built her wanted a single answer. Was nuclear power the future of the surface fleet, or an expensive mistake dressed up as one? Long Beach never gave them a single answer. She gave them 2 welded into the same hull, and left the fleet that followed her to decide which one was worth carrying forward. The reactor became the future. The radar became a lesson. Neither one made the other unnecessary.